view full screen?
I think I'm going to use this one. So, yeah. Okay, thank you. I'm going to just try to set up my timer here so I don't run late.
Guillermo, do you want the microphone so you can walk around for the recording?
Okay. Thank you. I was planning on staying here, but that's okay. Okay, thank you very much. 2 years ago, with the previous version of this workshop, which I think was only half of the room, started my collaboration with Larry Karin and his group. So I was one of more exciting and productive workshops I ever been because of that collaboration. So I'm very excited and thankful to be back here. So I'm going to talk about solving inverse problems with Gaussian mixture models. And from my view, it's the return of PCA. The first part of the work is joint work with Woshen Yu, a former postdoc in my group, and Stefan Mala. And then there are extensions, and I will point out the collaborators then. So the basic idea is very simple. We have an image, F, that we want to try to reconstruct, but we don't observe it. We actually observe Y, which is a degradation U of that image, and we add some noise, and examples are, we call it in painting. It's not exactly in painting, but it's just subsampling, where U is a masking operator. You have this other subsampling where you basically subsampling a regular grid, and then you reduce the size, and then U, the classical blurring. And from any of these, you want to go back to the original image. Okay? So that's the basic idea of the first problem I want to attack. I'm going to mention a problem not related to images just for a couple of slides, and then I'm going to present some theory at the end. So one of the approaches to address this problem is based on something that we have seen very often during the day today, and something myself and many others have worked, is to consider sparse models. So the whole idea of these inverse problems, they are ill-posed, so you have to assume a model on your signal. Image processing has been dealing with the question of image models for the last 40 years, and it's going to deal with this question for the next 500 years. So that's the most fundamental problem in signal processing, is to design useful models for your signal. And one of the models is sparsity, where basically your signal is a combination of two terms. One term is a nice linear combination of just very few atoms of a dictionary. Can be a learned dictionary, can be an off-the-shelf dictionary, but that's the basic idea. And then you have a deviation from the model. And note that I call it a deviation from the model. That's not noise, it's just deviation from the model. And the basic idea is that deviation has to have low energy. Otherwise, there is no modeling here. So that's a classical sparse modeling. And we are going to, it has been very successful in numerous inverse problems and denoising techniques and beyond image processing. I'm going to slightly deviate from that model, and then I'm going to try to come back to it. But the basic idea, once again, of this model is that the signal can be well approximated by a sparse linear combination of atoms, which means that the signal lives in the union of a very large number of subspaces. So here is my slide deviation for a couple of slides, but those that are familiar with this will see, but it's not really a deviation. But we're going to come back to that in a second. I'm going to have a collection of signals as before. My signals are going to be patches of images. So think about yi as an observed patch. Observed patch means that it has gone through blurring or something like that. So yi are all the patches on the image. And now, instead of assuming that they're a sparse model, I assume they come from a collection of Gaussians. Okay, one of the oldest models that people have assumed, and my claim is for inverse problems, have abandoned way too early. So this yi, this fi, sorry, come from one of k Gaussians. Okay, and I can explain you how we set up k, but have an idea is 10 or 20, just a small number of Gaussians. Okay, so every patch comes from a small number of Gaussians, and I observe a degradation of that patch. And now the challenge is to estimate the Gaussians from the degraded image. So no dictionary on the side, no training data. You have one very bad image, and you have to do all your job with that. So that's also the kind of work, that's in contrast with the kind of work I've been doing before on dictionary learning, where we have a database. It's more on the kind of work that Larry Karin and his group has been doing, where there is no pre-learning, you just have that data to deal with. So you have to estimate them. You have to identify which one of these 20 Gaussians is the correct one for Fi, and then from Yi, you have to reconstruct that image given that Gaussian, that patch. Okay? So it looks like a very complicated problem. It has been addressed a number of times in different fashions. Okay? And once again, all what you have is your degraded image. So we have these 3 tasks. This is, I'm going to write it in a second, the right formula for that, but this is a non-convex problem. And we are going to solve it with a EM type of algorithm, a particular version that is called a map EM. So it's a maximum a posteriori, and that's going to be clear in the next slide. And then as an EM type algorithm, we have 2 steps. In the E step, we assume that somebody gave us those 20 Gaussians, okay? Meaning the mean and the covariance. And then we estimate for every patch which is the Gaussian that you like the most, okay? That's a KI, that's a clustering. And we also, once we estimate that, we reconstruct the patch based on that Gaussian, okay? So that's the E step. In the M step, you just finish doing the clustering and the reconstruction, so you re-estimate the mean and the covariance. So it's the same type of k-means type of algorithm, and then you iterate. In all the results I'm going to show you in a couple of slides, we iterate between 1 and 3 times. So it's very, very simple iterations. So let's talk about the E step. In the E step, we assume these 20 Gaussians or so are given to us, and we do a maximal a posteriori, and that's written there. It's very simple. We are going to estimate the F and the K that maximize the log probability of F given the observation and the Gaussian. And I'm assuming for simplicity of the notation that I basically normalize so the mean is 0. So once again, this is your observation. I'm on the E step, so I assume that I know the covariance, and I estimate the maximal probability of the signal given that observation, that covariance. When you write that you assume that F comes from a Gaussian, and you assume that your noise is Gaussian, you get that this is equivalent to this. So this is just pure algebra. So if you're not too familiar with this type of Bayesian type of estimation, it's about 2 lines of algebra. So this comes from the fitting, and this comes from the Gaussian model. So this is for the noise. This comes from the Gaussian model. Okay, so here is where the covariance. This is a term that for some reason it has disappeared from many papers in the literature. And it's a very important term. So this term comes because I'm not only optimizing for F, I'm also optimizing for K, for the best of the Gaussians. And this is a term that measures the complexity of your model that you pick. The more complex, you have 20. So this is encouraging you to pick the simplest. And simplicity is given by the covariance. So the people in the audience from information theory, and there are many that are much more than myself, will not be surprised that you have to pay a penalty for your fitting and for your complexity. How do you solve? This is a quadratic problem. It's solved by Wiener filtering. Very simple. You go through each one of these 20, and you say, what will be my best estimate if you were my best Gaussian? So this is dropped, because for a second I'm fixing which one of the 20. So this is, let's say, number 7. So this term is dropped. You have to optimize for this. This is a Wiener filter. Okay? Nothing can be simpler than applying a Wiener filter. Okay? And you do that for each one of the 20, and then you plug back on this equation to take into account the complexity of the model, and you pick the one that gave you the minimum. So you pick the one that gave you the minimum reconstruction with this formula plus the complexity. Okay? So that's what the MapEM tells you to do. So 20 Wiener filters. And I have done my clustering and my reconstruction. Okay? So that's the E step. In the M step, I just finished doing the clustering and the reconstruction, so this is the same as k-means. I have to re-estimate my average and my covariance. And you can show that, that what you have to do is the maximum likelihood is basically the empirical mean and the empirical covariance. That's the optimal. So you have to average the signal and get the empirical covariance. And there is another important thing here, and every one of these things, taking into account the log covariance, taking into account what I'm going to say next, is very important for this to be done right, is that you're estimating covariance of, let's say, if you're on 8x8 patches, you're estimating covariance of 64 dimensions, with just a few thousand samples, if you're lucky. So you have to regularize. You have to go into the literature of how you estimate robustly a covariance matrix. It turns out, and we talk with a few experts, they say there's nothing simpler, and often the one that works the best is just to add a bit of identity to your covariance estimate. Okay? There is a lot of theory, but in practice, this works fantastically well. Just to make sure that the inverse is well posed. So that's it. 20 linear filters and empirical covariance, and you iterate between 1 and 3 times. That's a whole algorithm of map-EM, assuming that basically my signal belongs to a Gaussian mixture model. Before I go into examples, I want to spend 2 slides bringing you back to sparse models. So Gaussian mixture models and PCA are exactly the same. Okay? So basically, you take your covariance and you do an eigenvector decomposition. You get the BK, SK, BK, where BK are the eigenvectors and SK are the eigenvalues. So you take your signal and you rotate it to the basis of the PCA. And then if you remember what we had before, this is our optimization before, but now I'm going to change for this representation, I get this. So estimating your signal in the original Gaussian mixture is like estimating the coefficients in the PCA that is derived from the covariance matrix. So you can play with the one that you like the most. Okay? So these are two the same. So now I can connect that with sparsity. What did we have for sparsity? For sparsity, you have a dictionary. And the idea was that you are going to try to encode the coefficients that represent the best your signal with that dictionary, and you add an L1 or an L0. And what happens, so you pick a few, and what happens is that if that your dictionary is of size gamma and your sparsity is lambda, you get lambda taken from gamma options for your subspace. To give you an idea, in images with 64 dimensions and dictionaries of 256 and sparsity of about 10, that gives you 10 to the 14 different subspace to represent your signal. So when you're doing regular sparse modeling, you are picking one subspace out of 10 to the 14. That's more than pixels in the image. Okay? And that makes the problem quite unstable, in addition to, in spite of all the excellent algorithms that we saw today and we're going to see more tomorrow, still not at the level of an FFT. Although computation, it looks like at the level, it creates, and we have to be a bit careful, and that's why people have been doing great work. Now, what we end up, if you do the interpretation of the PCA, is with this. Every Gaussian is a PCA, so we end up with 20 blocks. My selection says you have to be one of those 20. So I went from 10 to the 14 to only 20 options. Okay? And you don't do exactly this because the solution of this is a Wiener filter, but if you want to look at the optimization, it's kind of a weighted L2 on the PCA basis. It's not the regular weighted L2 that you see in the sparse coding optimization, because the weight here are collaborative weights coming from the eigenvalues of the PCA. So we went from regular sparsity to block sparsity, actually a particular case which is called one block sparsity, and moreover, every block is a PCA. So the estimation on every block is linear, and then we pick the block by doing a max. So it's a pseudo-linear approach. So it's 20 linear operations and one maximum to get the code. So of course, this is all nice, but we have to show that it's useful. Otherwise, it's yet another model that is simpler than sparse modeling, but is it good? So before I show you some experiments, let me just show you some clustering. So in the first iteration, we randomly cluster all the patches. We work with overlapping patches. We just randomly throw them to each one of these 20. Basically, we use 19 PCAs, and that is related to the discretization of your angles in images. And then we let this run, and very fast, it basically just accommodates itself. So the color codes here indicates the clusters. And now I'm going to just show you results without showing you. We have, Washington did a fantastic job of comparing with everything we could get our hands on. So we have like very long and kind of boring but important tables, but I'm skipping that. I'm just showing you results. So this is, the U is a masking operator, and you can see a bunch of results, and both quantitative and qualitative, this piecewise linear estimator is better, and is orders of magnitude faster than basically any of the algorithms that we compare with, because we just do a Wiener filter. Okay, actually we do 20, 19. Okay, so this is just for color, the same, just the reconstruction. So this is the kind of images that Professor Debeshi showed early on. We also do zooming. So this is just changing the U operator. And once again, this is the result. So just to show you qualitative, you get much nicer edges, and quantitative, they're better results. And everything we compare to is either has been considered state-of-the-art for a long time, or is very recent algorithms. So we try to be as fair as we could. If we miss an important algorithm, please let us know. And I'm going to point out where to find the paper in a second. There are also results for the blurring. Again, because it's the last talk of the day and we're all tired, I'm not going to bore you with the tables. Just giving you a glance that this is very generic for all these inverse problems. And of course, we can do denoising, where basically the U is an identity, and the results are also very good. So we were working on this, and we got to this extremely simple model. And the results for a lot of inverse problems in imaging were really, really good. And then we were extremely curious to see if we were lucky to be working for the last 15 years on image processing. Maybe it's an easy problem to do inverse problems in image processing. So let's take an inverse problem in a completely different area and see if this very simple model can do something there. So I was extremely lucky to have this undergrad student, Flavien Leger, coming from Paris for a summer. And it was kind of risk-free. He's an undergrad. For an internship, he doesn't have to have a paper at the end. He has to learn. So we say, OK, learn our paper, learn PCA, learn GMM, learn all this, and let's try apply this to matrix completion problems. Okay? So we got 2 of the standard data sets for the movie rankings, and you have, this is a classical problem we are going to hear much more tomorrow, but we have a matrix full of holes. The matrix has users, movies, and then rankings, and then you have to fill in what's missing. For one of the data sets, there is only about 4% of the matrix available, the other 4.6. And you have more of the numbers here. And this is the result we got. The lower the number, the better. So this is a result by Larry that he presented in a paper, if I'm correct, about October last year. And it's the best published result to my knowledge. But we are very close with a model. Where's Larry? He can agree or disagree with me. With a model that is significantly simpler. And I'm going to make a comment about that in a second. This is a paper, for example, by Michael Jordan, published at ICML, one of the most prestigious conferences last year, with an extremely complicated model. And we basically are either better or outperform it with just a Gaussian. It sounds surprising, okay? And this is just another data set where we share the top results that were published until then with Larry. And so this was surprising that such a simple model was achieving state-of-the-art results, not only in image processing, but also in matrix completion problems. And then the next step, of course, was to say why. And can we build any theory on that? And that was our concern with Washington. And to introduce my last slide, so once again, we are running all these inverse problems with an extremely simple model. And I have to warn you, it took us a while to get to that simpler model. I would be more than happy to explain to you where we started before this talk. And it was much more complicated, but we kept simplifying it, simplifying, and gaining speed, and gaining results, and gaining cleanness in the algorithm. That's my 20 minutes mark, so I'm going to almost be done. So we were very, very curious with Washem to try to explain this, and I'm going to explain that in my last 2 slides. So for a long time, we live, and we still live, in the band-limited world. And the basic idea of band, if you know your model of signals are band-limited, then you do Nyquist sampling, linear reconstruction, and you're done. Then came the era of sparse signals and the theory of compressed sensing. And we moved to nonlinear reconstructions, which in my view, no matter how hard we work, are going to be more difficult than the linear. And Professor Dabeshir made that distinction very clear in the morning, linear, nonlinear. These slides were prepared from the morning. So now I show you that with GMM PCA, we do a piecewise linear. We are not yet here, but we are better than here. So the question is, can we build a sensing theory? We had Nyquist, we had compressed sensing. So what happened when we assume a GMM model? So here is, in one slide, the recapping of the theory that we built, and the papers are on arXiv. We started to build a theory of statistical compressed sensing where we assume that the signal is sampled from a distribution. So no sparse or no band-limited, sampled from a distribution. And we are not interested in reconstruction of a signal, but on reconstruction on average. And that's very important because in image processing and in audio, we work with overlapping patches. So we don't care exactly about everyone. We care about when we average things. In 8x8, we end up averaging 64. So our theory, some of the results, I'm just giving you a glance. And by the way, we prove all our results basically extending a fabulous paper by Albert Cohen and Ron DeBoer on K-term approximations. You can go through their papers and just change the model, follow their proofs, and get the proofs of our results. We do not have to prove the optimality of the L1. We have the map, linear optimality. But that beautiful paper helped us a lot to get to our results. So we show that we don't need K log N over K as in compressed sensing. Only K measurements are sufficient for this model, where K is the order that you want to get as close as possible to the best K-term approximation. So you tell me what's your best K-term approximation, and you only need K to get there with a probability, which is actually the probability of failure is much, much smaller than in the standard CS. So this is for a single Gaussian, okay? So for a single Gaussian, it's a win-win situation compared to sparse modeling. Faster, simpler, less samples, better probability of reconstruction. Now, you can actually consider, this is slightly more elaborate. Instead of looking at RIP condition, you can consider a probabilistic RIP condition and get even better results, with the advantage that you can actually compute all the constants. The problem with the RIP is that you cannot compute it. But in our case, you can compute. Everything is statistical. So there is an expectation before every formula in our paper, and that makes our life much easier. But I show you with the results that it makes the results even better. So why not use it? So this was all for Gaussian. And once again, I will be more than happy to discuss more about the results, but the paper is available. And then for Gaussian mixture models, all what was left to us is from the sample data, what are the chances to fall on the right Gaussian? Once I'm in the right Gaussian, I'm in the original framework. Sorry. Okay? So we also have closed formulas for the probability. How many samples do I need to fall on the right Gaussian? Basically, to do the right selection. So once again, we can discuss this more, but the conclusion of this is that this model that also produces excellent results actually has theoretical advantages over other models. So my summary is that we introduced these Gaussian mixture models and a very simple map EM for inverse problems. We end up with a piecewise linear estimator that has a kind of a structure sparsity and collaborative filter. It's very fast. I want to mention, and also we have this new statistical compressed sensing theoretical results to support the theory. I showed that we can move beyond images with this matrix completion, and I think part of the fun of this conference are going to be the posters tomorrow evening. I look at the list and they are superb. One of them is actually by my students on extending these models also to audio, and the results are also really interesting. So I encourage you to go and see all the posters. I look at the list, they're just superb. The papers are on archive, and just a bit of ad for students. We have openings in my group and with collaborators for postdocs as well as visitors. If you just want to go, come and freeze, just let me know. We will be happy to have you. Okay? Thank you very much. I probably went a minute more. But yeah, I think I can hear you, but I'll let you know if. Yeah. The question is why not to use the EM and to use the map EM? Okay. So that's a question that we were kind of curious, because the map EM is forcing me to select one block, and we actually try. So it's simpler to select one. One block sparsity makes our life easier. The blocks are non-overlapping. We try, and it was not necessary, okay, to go beyond that for this problem. There might be for other problems that we need to go into more of the standard mixture of Gaussian standard EM. For this, we didn't find it necessary. We were curious about that. We tried. It just didn't get as much. Oh, yeah. So sensitivity to everything I haven't told you, okay? Yes. So the initialization, we actually have a very long discussion in the paper on that. It depends a lot on the problem. So masking is one of the simplest problems. Do whatever you want with the initialization, and you're going to get the same results. Deblurring is one of the most difficult problems, inverse problems. In that case, I'm going to tell you what we do. We create a bunch of random-oriented binary patterns. We randomly blur them, okay? And then those that were on the same orientation, we do a PCA, and that becomes my initialization for my covariance. So it's very simple, but if we don't do that, if we just do random on deblurring, results are not as good. They're not a disaster, but they're not as good. For simple problems like masking, simpler, I'm not saying, you just do whatever you want and you get okay. And we have even the experimental results in the paper we discussed, and those are important. The number of PCAs is not very relevant as long as you have quantized correctly. That's why we do 19, which is the least. We do 18 orientations plus I call it a garbage collector, but that's a technicality. Yeah. Yeah, and yeah. So you say what's K and what's N?
Yeah, when you compare this, gross order big O notation, it would be hard for me to believe that if you had just a patch and you have order 20 samples out of that patch, you can reconstruct that patch.
Yeah, don't forget that. So yeah, so K is the K-term approximation is about 10. And N is about 64. That's a patch. That's why I didn't discuss, but I showed the graphs so we can discuss. We simulated that. We didn't just say, oh, the theory tells us we should. Big O are big misleading things very often because there are constants in the big O's. So it's manifested actually in reality. But don't forget that in that case, in the first case, I assume that my signal belongs to a Gaussian. A Gaussian is very well ordered okay? And Gaussians for real images not only are very well ordered, but the eigenvalues decay very fast. So although I'm not in a subspace, I'm in a potato, in a pancake, okay? Because things are very, that means the decay is very fast. I can show you the eigenvalues. So you are on a very constrained space, but that works. It's very constrained. It's a 64-dimensional, but with extremely fast decay. After like 5 to 10 eigenvalues, things are gone. They're ordered, something that doesn't happen in regular sparsity. You can have things every place. Now we know that we are not only block sparse, but inside the blocks, because of the pre-order of the PCA, we know where is the importance. So there is a lot of structure in my model, much more than in regular sparsity, much more than in structure sparsity. But it looks like it's powerful enough still to do very good in reality. So that's why it's not surprising. It's because of the amount of structure that my model has.
So my comment actually was not, I mean, the quality of the results was spectacular. It's just that these ordered table again, it kicks in when n goes to infinity.
Yeah, n is the size of the patch.
Regime for the sampling theorem for this particular problem works in small n.
So I take that and I'm going to do this as my home take message of, let's say, that section is, if you want to call it same order of samples as compressed sensing, much simpler reconstruction, better results, higher probability of success. So, but that's what the result tells me, all because the model is so restricted, but it's still useful. If it weren't used, it's realistic. That's why it's surprising. I'm still surprised. Every cluster has its own covariance. And every cluster is just a tiny bit of epsilon for everybody. It's the same. For all the examples, we haven't touched that parameter. We just put, I don't know, 0.05 of identity for every single image we have done in the last year. We could. It's interesting, and it's a long discussion, but we talked with a couple of guys that have long papers on this and say, first of all, just try epsilon identity. So, but yeah, it's very stable, and yeah.
I think that the further discussion should be done in smaller groups. So.
Thank you very much. Thank you.
So I just wanted to remind everybody about the Nasher reception tonight in case you missed Larry's announcement this morning. The bus is going to leave from the front entrance of the inn here, starting at 6:50, and it's going to run a continuous kind of loop between here and the museum, and it's only maybe a 5-minute drive away. It's even walkable, except that it's so hot. And the program says that it's hors d'oeuvres, but I told the caterer I wanted it to be enough hors d'oeuvres for Guillermo-sized people to have a full meal. So there will be plenty of food, vegetarian options, a nice selection of beers and wines, and don't forget a free drink ticket on the back of your name tag. Please bring it with you. All right, thank you. Bye.